Thank you, and welcome to our talk. So a bit of background information on us. We are two software developers. We have lots of experience in voice over IP monitoring because we used to work on a startup that was doing just that, a voice over IP monitoring product. This startup was acquired first by Acme Packet, which at its turn it was acquired by Oracle. And then we started to work, the two of us started to work full-time on this Packetbeat project that we're going to talk about today. And because we are on the scale track of the conference, I'm going to start by talking about scaling a little bit. And there are two aspects of scaling that I find interesting. One is the technical side. As your startup has a lot of success and you want to reach more and more users, you will scale your infrastructure to tens, hundreds, thousands of servers. At the same time, there's the organizational aspect, in which, as you grow your company, you scale to hundreds, thousands, and tens of thousands of employees, maybe engineers, product managers, marketing people, and so on. And it's interesting that these two aspects of scaling are actually closely interlinked. They are linked by what's known as the Conway's law, which says that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations, right? So what often happens is that at the beginning, the organization looks something like this. It's split into a UI team, a backend team, a database team, and so on. And the system that they produce also looks like this, right? This is how it happens. As the company grows, they start to realize that this doesn't scale very well, and for multiple reasons. But one of the reasons is that when a new feature comes up that needs to be implemented, it affects all these teams and all these parts of the systems. So you get a lot of interlocking between them and lots of communication overhead. So that's why in the more recent years, people have started to adopt microservices. They are used successfully by companies like Netflix and Spotify and so on, where they split the functionality of the overall service in lots of small services, and you have small teams working on them. So each of these services are self-contained. They talk between themselves with an API, so they can be simple. They can be written in different programming languages, which is a good way of bringing fresh technology in your company. And everyone is happy about this usually. And while each of these systems by themselves are very simple, the overall system can get quite complex, right? The complexity is not removed, it's more like moved into the communication between them. And in fact, it often happens that things get so complex that no one in the company has an overview of really what's going on with the whole system. And is that a bad thing or is that a good thing? I think it's a good thing, and I think we have to accept the fact that if we want to create truly advanced systems, they will be more advanced that any of us can understand them, even if we help creating them. And in fact, I think this is how, if we do read this right, this will resemble the way evolution works, right? Just like the DNA evolves to adapt to new environments by mutations, you have your system which adapt to new requirements using Git commits and pull requests and so on, right? And it's important to choose the right mutations, because if you choose the bad mutations, you're going to be extinct as a company, right? Or you will become a rat or a kitchen bug or something like this that's not very pleasant. On the other hand, if you choose all the good mutations, you will become maybe one of the greater apes, or a dolphin, which is the most intelligent life form on Earth. Okay, and how do you choose the good mutations from the bad mutations? There are, of course, multiple approaches that you can have, but I think one of the things that's really important is monitoring. You need to define a set of KPIs. Also, on the business side of things, you have KPIs, and you apply mutations, and you see if things are going well or things are going bad. And equally, on the technical side, you should monitor things like response times, latency when, availability, error rates, and so on, so that you know when things are going well and where things are not going well. Also, when things are not going well, you want to be able to identify the mutations that are problematic, so you can remove them as soon as possible. So, because we recognize that this problem is both very important and also difficult, we decided to work on this, on monitoring and troubleshooting distributed applications.
OK, now let's see what are requirements for this kind of monitoring solution. So it should be scalable and reliable. I would say it needs to be more scalable and reliable than an application in monitors. It has to extract data from different sources. It has to have low overhead. We don't want to question if we want to enable monitoring or not. Low configuration. In a highly dynamic infrastructure, servers go down and up, and we don't want to do any manual configuration. And it should be simple and easy to understand. So everyone from the company should be able to interpret what the monitoring system it shows. So we think a good start for monitoring solution is to look at the communication between the components. Distributed systems nowadays, they are very different one from each other. They use different programming languages, different frameworks, even different operating systems. But what they have in common is that the communication between them is using the network. And the protocols they are using are more and more standard. For example, they use HTTP APIs and different RPCs like JSON RPC, Thrift RPC. They are also database protocols like MySQL and PostgreSQL and so on. Packet data is objective, so we don't have to rely on the logs when we want to debug an issue. And no latency overhead, so it works, the monitoring solution, it works by having a looking at the copy of the traffic. OK, so we started the Packetbeat, and the Packetbeat project, it was launched almost 1 year ago. It's open source. It's written in Golang. Yeah, so let's see what is Packetbeat. So Packetbeat consists of Packetbeat shippers that are installed on an application servers. They follow the TCP streams, decode the upper layer protocols like HTTP, Redis, MySQL, PostgreSQL, Thrift RPC, and so on. Then they correlate the request to the response. And they get data and measurements from the transactions and also from the environment, and generate a JSON object for each transaction. Here is an example of a JSON object. This is a select query to a PostgreSQL. As you can see, the method is select. The number of rows returned by the query is 2. Response time is 12. And the size of the response is represented in bytes out. So we have all these shippers installed in your system, and they are collecting a lot of data. What do you do with the data? What can we analyze it? How can we analyze it? So the traditional way to do this is first you decide what metrics you want to measure. For example, the number of requests a server can have, or the number of the response time percentiles. Then you write code to extract the metrics. And then you store them in a database. For example, it can be a time series database. And if you want to drill down to look at the transactions that cause an issue or a peak, then you have to store the transaction in a database. And this time, this database can be a normal database. And features like drilling down and top-end queries are very difficult to implement in the traditional way because you have the metrics and the transactions stored in different way. So our solution to this is to use the ELK stack. and to push all the generated JSON object to Elasticsearch. And here we have optionally, you can use Redis and Logstash to have a bit of buffering before inserting the Elasticsearch. Additionally, you can use Logstash for changing the data. For example, if you want to add a new tag or you want to change a field name, you can do that with Logstash. And if you want, you can also configure Packetbeat to insert the data directly into Elasticsearch. On the top of the Elasticsearch, you can use Kibana to visualize the data. Yeah, so why did we choose ElkStat? Because it proved to be a good solution for logs, and our solution is more or less similar with this. And it's scalable. It proves that there are installations with more than 1 million events per second. It offers a clear and simple flow for the data. First, you have the shippers that are generating the data. Then, optionally, you have the Logstash that are transporting the data. Then you have the Elasticsearch that are indexing the data, and Kibana to visualize the data. And the most important one is that you don't have to create the metrics beforehand. And it comes with features like drilling down and top-end features out of the box.
All right, now to the visualizing part of the data, which is more fun, I think. So we're using Kibana 4 for visualization. This is the Discover tab for it. You might know it. And we just show here how easy it is to find all MySQL errors, for example. Right? We put a filter on status not OK, and a filter on type MySQL, and there you have it. You can also, of course, do free text search because, well, it's Elasticsearch, so we can search. Packetbeat also comes with a set of predefined dashboards, right? So usually when you use Kibana, you start with a blank page, and you have a bit of work to create your widgets and so on. But with Packetbeat, because we know exactly how the data looks like, we can predefine some of these dashboards for you. So then you have some pretty good examples for Kibana dashboards that you can start from. For example, here in the first row, we have a simple count of the different transactions types. So for different protocols, HTTP, database, RPC, and so on. And on the second row, we have some a little bit more advanced visualizations for response times, based on the response times. And actually, that's what I want to go a bit deeper into. For example, this one, the percentiles values over time. They are done in Elasticsearch by combining the date histogram with the percentiles aggregations. In general, if you have a monitoring solution that gives you just averages for things like response time or load time or delay and so on, that's not very good, right? Averages are really not good for that thing. It's much better to use things like percentiles. And luckily, in Elasticsearch, there's the percentiles aggregation, which does exactly that. This is how the request looks like. You just give it the field where the data is found. In our case, in the Packetbeat data case, it's called response time, and the percents that you want. And this is how the response looks like, right? You just get aggregation and free values. One thing you should know is that the percentiles aggregation is using an approximate algorithm. It's T-digest by Ted Dunning. And the funny thing is that Ted Dunning has a talk at Berlin Buzzwords, I think right here just after lunch. So I'm not going to talk too much about this. But what you should remember is that it's an approximate algorithm, but its properties make it very, very convenient for this type of data that we have. OK, and as I said, we need to create that graph. We need to combine it with a date histogram. And what the date histogram does is just splits your time interval in a your data in small time intervals, small or large. In this case, we use 1 minute, but it's important to note that it can actually be 1 second or 1 millisecond. So there's really no limitation in the resolution you get on graphs, which I think is pretty cool. All right, and if you send that request, you get a response like this. The key is always the start of the interval, so of the time interval in this case, and the doc count is included by default. And in order to produce that graph, we combine the two. So you have a date histogram, and nested within it is the percentiles aggregation that we saw before. And if you put them together, the answer looks like this. So now you have a list of intervals, and for each intervals, the free values for the percentiles we requested. OK, so if you plot that, it looks like this, which is what we wanted to start from. Now the Kibana config for that, it's also very simple. On the y-axis, you select the percentiles, and on the x-axis, you select the date histogram. And this is how Kibana creates the request, very similar with what I showed you before. And you get that graph. All right, your turn.
OK, so this is a latency histogram that shows this is a good way to show you an overview of the response time of your application. For example, in this diagram, you see that most of your requests are answered in less than 40 milliseconds, and there are a few that take up to 60 milliseconds. To implement this in Elasticsearch, you create a histogram aggregation on the response time field within 10 milliseconds interval. And this splits the data in buckets by response time. And you have a bucket in the time interval from 0 to 10 milliseconds, and another one from 10 milliseconds to 20 milliseconds, and so on. This is how the request will look like. And the response that we get back contains the key, which is start of the interval, and the doc count, which is the number of transactions that are included in this bucket. If we put this in a graph, we get something like this. And we get a latency histogram that is constructed for the entire interval. But what if we want to see the evolution of the latency histogram over time? We can implement this in Elasticsearch by combining with a date histogram aggregation. And as you can see in the request, we have our latency histogram nested in the date histogram aggregation. And this is a response that we get back for the request. And it contains a list of objects for each interval. And each object contains all the buckets with all the values for the response time. And if we put this in a graph, we see something like this, where each bar is represented in a time interval, and the stacked colors represent latency histogram. If we want to configure this in Kibana, we need to set the y-axis to count and the x-axis to date histogram on time step, and also to add the sub-aggregation histogram on the response time.
All right. Another interesting feature that we make use of a lot from Elasticsearch is the aggregations where you do top 10 something, right? So you can do, for example, top 10 most frequent SQL queries, or top 10 slowest HTTP codes, HTTP requests, and so on, right? These are very useful for monitoring. And let me pick one of the examples here. It's maybe not the most visually appealing one, but it's very useful. It shows you the slowest RPC methods, sorted not by average. As I said, the average doesn't really make sense for this kind of data, but by the 99%, right? And the way that works is that it combines the terms and percentiles aggregations. The terms aggregation, it splits the data in buckets, like any aggregation does. But what's different here is that the buckets are dynamically built, right? It creates one for each unique value. And by default, it only returns the top 10 by document count, because, of course, there can be lots of unique values in the general case. Yeah, it's also important to note here that the counts are approximate because each shard might have a different opinion about what the top 10s are, right? So you cannot make it precise from that reason. But the good news is that Elasticsearch will tell you how big the error can be. So if you send this request, where you just choose field method and size 10, you get a response like this. And you see in doc count error upper bound, you get that in this case, there's no error that you should expect. And then you get the list of, as I did it here, without any ordering, just the default one by doc count. You get the most frequent RPC method calls from the data, right, which are calculate, zip, and ping in this case. But now, if we want to order it by the 99 percentiles, we can do that by using a sub-aggregation on the percentiles and use the order clause to say that which of these sub-aggregations we want to use and the order, descending or ascending. So if you send then this request, then the response will look something like this, right? So it's no longer sorted by doc count, but it's sorted by the response times percentiles. And you also get the values there, so you can use that to put into a graph. If you want to do this in Kibana, you choose the metric percentiles, and then you can, when you configure the terms aggregations, it offers you to order by it. So that's also very convenient. All right, before we move to the next thing, I just want to mention a couple of tips. One is that there is a live demo, demo.elastic.co/packetbeat, where you can see and play with this type of data. I also put the examples for aggregations that we have in this GitHub repo. And also, I wanted to mention that you should use Sense. It's a Chrome add-on. I have to admit, I learned way too late about it, and I was fiddling with Carl to do this kind of things. You should, yeah, just in case you don't know about it, you should really use it. Right, another tip is that when you use Kibana, you can always see what aggregations are sent. This was valid in Kibana 3 as well, but it also works in Kibana 4, so you can click on the arrow there and choose the request tab, and you can see exactly what aggregations are sent to Elasticsearch. So it's a good way of learning new aggregations. You just look how Kibana does it. OK, now let's talk a bit about the future. And as Monica said in the beginning, the problem we were trying to solve was about monitoring distributed systems, and we thought it's a good way to start with packet data, but that was always meant to be just the beginning. And actually, we wanted to add over time more sources of data, so like OS readings for CPU, memory, and so on, maybe code instrumentation, tracing, data from API gateways, or just internal stats from different servers, right? And we are talking with Shai Bannon, who you might know is a CTO of Elastic, the company behind Elasticsearch, Kibana, and Logstash. And we realized that we have quite a bit of a common vision regarding these things. So
we have some great news to announce that we recently joined forces with Elastic. And so Packetbeat is from now on is part of Elastic project, is one of the Elastic project, like Kibana and Logstash. And we also had to change a bit the mascot to include the Elastic bubble. And we are keeping the project open source. Moreover, we changed the license from GPL version to Apache. And yeah.
All right. Yeah, we can. Yeah.
So our mission at Elastic now is to ship operational data to Elasticsearch, not only packet data, but all kinds of data.
Right. So we came with this idea that we have now Packetbeat bit for packet data. We could have also file bit for log files, for example. This actually already exists in the form of log/forwarder, but we want to improve it and make it a real bit. And in the future, we can also have other bits as well. These are just ideas, but we could have like a top bit for CPU memory and so on, a metrics bit, which could use plugins like Nagios or Sensu does, or you can have a run bit, which comes from real user monitoring bit, which takes data from the browser. These are just different ideas that we could implement in the future.
Yeah, so if you want to stay in touch with us, we have a Twitter account at Packetbeat. We also have a forum at discuss.elastic.co/c/bits. And also we are preparing for the webinar, and we encourage you to sign for our webinar. The webinar will be a bit different than our talk. It will contain more practical hands-on, like how to configure Packetbeat, how to run it, and so on. So feel free to sign up.
All right, and that was it. If you have any questions.